Hello everyone, I just came from our physics class wherein we solved just one problem for the entire period. Anyway, this is on chapter 25 on current resistance and the electromotive force. Now, in the previous chapters, we have studied charges at rest, electrostatics. Perhaps already when they have achieved or attained a state of equilibrium. Now we're ready to study moving charges. Firstly, we're going to look on a problem regarding the theory of metallic conduction. We're going to solve for the mean free time tau of electron-electron collisions in a certain material and see how that relates to that material's capability to resist or allow the flow of current. In honor of those in the medical profession, I have decided to choose to make my last two problems relating to human biology. Firstly, we're going to look at the treatment of heart failure. We're simply going to solve for the amount of power or energy coming from a defibrillator to a certain person's body. And lastly, we're also going to discover what damages will our body incur after being struck by a bolt of lightning, if it's at the very least possible to survive a lightning strike. We'll see. Our first problem, 25.49. Pure silicon at room temperature contains approximately 1 times 10 to the 16th free electrons. Note that free electrons are different from the electrons at in the valence shell of an atom. Free electrons are not valence electrons. Contrary to what I actually thought, I actually thought that free electrons are just another term for valence electrons, but they're different. They're actually not attached to the atom. They're free electrons. So 1 times 10 to the 16th free electrons per cubic meter for pure silicon. Referring to the table, calculate the mean free time tau for silicon at room temperature. All right. Now, we can express, make an expression for the mean free time in terms of mass, in terms of mass, positive integer n, E, and also rho. Now, looking at this table, resistivities at room temperature, we'd be needing the value for rho. We have here pure silicon, 2,300 ohmmeters. Plugging that into the equation, we get 9.11 times 10 to the minus 31 kilograms. I highlighted in green what we are assumed to already know by heart. 9.11 times 10 to the minus 31 kilograms is the mass of your electron. We divide the mass by n, your integer, 1 times 10 to the 16th electrons per cubic meter, times 1.60 times 10 to the minus 19 coulombs. We square that, times 2,300 ohmmeters based on our table. And we get an answer of 1.55 picoseconds. 1.55 times 10 to the minus 12 seconds, the mean free time of collisions in pure silicon. So approximately 1.55 picoseconds. That is the time, the average time that a free electron is actually free before it hits another electron. And our equation here, that the very first line that we started with, it actually makes sense. Kilograms over per cubic meter times coulombs squared times ohmmeters. Those units actually cancel and give out only seconds. So we are talking about the right dimension, or the right quantity here, seconds, which is time. Now, why then does pure silicon have such a high resistivity compared to copper? The mean free time is inversely proportional to the number of free electrons, and that makes so much sense because the more electrons there are, the more likely, or the more often, an electron would be hitting another electron, right? So we have an inverse relationship here. Silicon has a fewer number, n, of free electrons than copper. Alright, now we jump to our second problem. A heart defibrillator is used to enable the heart to start beating if it has stopped. It returns the heart its normal function, because there are instances wherein the heart has an irregular rhythm. This is done by passing a large current of 12 amperes through the body at 25 volts for a very short amount of time, usually for about 3 milliseconds. We're asked to find what power comes, what amount of power comes from the defibrillator, and then delivered to the body, and also how much energy is transferred. Now we have, I'm going to introduce here another equation. P equals VI, voltage times current. P equals I squared R. P equals V squared over R. And we're going to use the first one, P equals voltage times current. And this makes a lot of sense. Volts times amperes is joules per coulomb times coulombs per second. We get joules per second, and joules per second is power, watt. It's a watt. And plugging in the values, we get, we simply multiply 25 volts by 12 amperes to get 300 watts. And that is the amount of power delivered to the body as doctors, or as surgeons, try to get the heart of a patient back to its normal bodily functions. For letter B, we're asked to find energy. That would simply be 300 watts times time, which is 3 milliseconds as given, or 3 times 10 to the minus 3 seconds, tenths, hundreds, thousands. And we get an answer of 0.90 joules of energy transferred. Alright, for our final problem, I was quite intrigued when I saw this problem. I was quite excited to solve for this one. Let's say you're struck by lightning. Lightning strikes can involve currents as high as 25,000 amperes that last for about 40 microseconds. If you were to be struck by a bolt of lightning with these properties, the current will pass through your body. We shall assume that mass is 71 kilograms, and that you're also wet. Perhaps you're drenched in rain, and therefore you have a resistance of 1.50 kiloohms. That is approximately your resistance. And although this is a rough approximation, it's a plausible approximation. By how many degrees centigrade would this lightning bolt increase the temperature of 71 kilograms of water? Given that the internal body temperature is about 37 degrees centigrade, would your temperature actually increase that much? Why or why not? And what could actually happen to you? So I highlighted our given here. Since we are looking at temperature change delta T, electrical energy becomes thermal energy. Therefore, representing electrical energy as U equals PT, or U equals I squared RT. We use the second equation. We square the current, 25,000 amperes squared, times 1,500 ohms, times 40 times 10 to the minus 6 seconds, or 40 microseconds. And then we get a value for electrical energy of 3.75 times 10 to the 7th joules, or 37,500,000 joules. Now, this electrical energy is turned into thermal energy, and we will represent thermal energy by Q. Thermal energy is denoted by Q. U is simply equal to Q. U equals Q. And solving for delta T, we get an expression of Q over mass times the specific heat of water. And then we get this equation. Now, in my previous videos, I have told that it's a good practice to always solve for things in variable form first. But in this case, I simply decided to write the value for electrical energy immediately, because it's the value is exactly 37,500,000 joules. But it's always better to solve for things again in variable form. But in this case, it's exactly this value, so we don't have any problems there. 37,500,000 joules divided by 71 kilograms, which is the mass of the person, or being also, as assumed, the mass of water, times the specific heat of water, which is 4.186 joules per gram degrees Celsius. We're talking about kilograms here, so that's 4,186 joules per kilogram degree Celsius. Then we get a delta T of 126.17 degrees centigrade. That is a very, very high temperature increase in such a short span of time. And in the book, in our reference textbook, University Physics with Modern Physics by Young and Freedman, your answer is actually 127 degrees centigrade. But I think they used 4,190 for the specific heat of water, and I used 4,186. Don't have any problems there. Finally, immediately after being struck, the heart's rhythm is disrupted, resulting in cardiac arrest, which is the leading cause of death for lightning strike victims. A person could also have a seizure or suffer from respiratory arrest. Given that the initial temperature of the body is 37 degrees, water would be vaporized almost instantly, and there would be much less of a person's mass or material left. So very high damages to the body will be incurred if you were to be struck by lightning. So that's all for this chapter. Thank you very much. I'll see you in my next videos. Feel free to visit my website at jdanielcudo.wordpress.com. I have there my some articles on science as well. Thank you very much. I'll see you in my next videos.